What if everything you see, everything you know, is a lie? Not some philosophical word game, but a physical reality. It's an idea some scientists are taking seriously, that our universe exists in a false state, a kind of cosmic mirage that could shatter at any moment. If it does, a bubble of true reality will expand at the speed of light, and everything we know will be replaced by a cosmos where we could never exist. This isn't science fiction. It's a possibility rooted in the most fundamental and well-tested theory of reality we have ever devised, the Standard Model of particle physics. At the heart of this unnerving idea is a single particle, the one that gives substance to our world and makes existence itself possible. Today we're journeying to the very edge of reality to ask, what if that same particle, the famous God particle, also holds the key to our ultimate destruction? This is the story of the Higgs boson and how it could, in theory, pull the plug on the entire cosmos. But don't panic. This is a journey into the deepest mysteries of reality, not a doomsday prediction. It's a story about the profound fragility of a universe and the astonishing fact that we are here at all to wonder about it. Before we can get our heads around how the universe might end, we have to appreciate the miracle of how it's built. Just look around you. The chair you're on, the screen you're watching, the air you're breathing. All of it, from the biggest galaxy to the tiniest speck of dust, plays by a very specific set of rules. We call them the laws of physics. These laws aren't just friendly suggestions. They're the unyielding source code of our reality. They set the speed of light, the pull of gravity, and the ways particles have to interact to build everything from atoms to people. For centuries, our greatest quest has been to figure out this cosmic rulebook. And amazingly, we've done a pretty good job. The crown jewel of this effort is a theory with the deceptively simple name of the Standard Model of particle physics. It's no exaggeration to say the Standard Model is the most accurate and tested scientific theory in human history. It lays out all the fundamental particles we've ever found, quarks, electrons, and the rest, and the forces that boss them around, with the exception of gravity. Think of it as the universe's character sheet for a game of cosmic D&D. Every particle has its stats, mass, charge, spin. Every force has its strength. For decades, this character sheet has predicted the outcome of every experiment we've thrown at it with stunning precision. But there was one stat on that sheet that was, for the longest time, a total mystery: mass. Why do particles weigh what they weigh? Why is a top quark as heavy as a gold atom, while a photon has no mass at all? For reality as we know it to exist, for stars to light up and planets to form, particles need mass. Without it, there'd be no atoms, no chemistry, no structure, no S. The Standard Model had a theoretical answer, a brilliant idea from the 1960s. It predicted a new, invisible ingredient in the universe. Not a particle, at first, but a field. An invisible, all-pervading energy field that fills every cubic millimeter of space. From the void between galaxies to the gaps between the atoms in your body. This field was the missing piece that would explain where mass comes from. But for almost 50 years, it was a ghost in the machine, a mathematical requirement with zero physical proof. The hunt to find it would lead to building the largest machine in human history, and its discovery would not only complete our picture of the universe, but also reveal the very mechanism that could, one day, tear it all apart. To understand the lie we live in, we first need to understand the architect of our reality, the Higgs field, and its quantum messenger, the Higgs boson. Imagine you're walking through a packed party. If you're a nobody, you can weave through the crowd easily, barely bumping into anyone, and get to the other side fast. Now, imagine you're a huge celebrity. The second you step into the room, people swarm you. They want a selfie, an autograph, just a second of your time. This crowd creates drag. It makes it much harder for you to move. You've become, in a way, heavier. This is the best analogy for how the Higgs field works. The Higgs field is that party, filling the entire universe. The different fundamental particles are the people trying to get across the room. Mass is just a measure of how much a particle interacts with this field. Particles like the photon, which carries light, are the nobodies. They don't interact with the Higgs at all, so they feel no resistance and shoot through the cosmos at the ultimate speed limit, the speed of light. They're massless. Other particles, like the electron, interact just a little. They pick up a small entourage of interaction, giving them a little mass. And then you have particles like the top quark, the heavyweight champion of the Standard Model. The top quark is the A-list celebrity in the room. It interacts intensely with the Higgs field, gathering a massive crowd that makes it incredibly sluggish and gives it an enormous mass, comparable to a whole atom of gold. Without this cosmic stuff, this universal field giving substance to things, the universe would be a thin, boring soup of massless particles zipping around at light speed. No atoms could form because electrons wouldn't be captured by nuclei. No stars would ignite. No planets would take shape. The very existence of matter, of solid ground beneath our feet, is a direct result of the Higgs field. For decades, this was just a great theory. But how do you prove an invisible field that's everywhere? You can't see it or taste it. The answer? You hit it. Hard. In quantum physics, fields are the fundamental reality, and particles are just ripples or excitations in those fields. Picture a calm pond. The water is the field. If you tap the surface, you make a ripple. That ripple is a particle. The Higgs field is no different. If you could cram enough energy into one tiny spot, if you could tap the Higgs field hard enough, you should create a ripple. That ripple, that fleeting vibration, is the Higgs boson. Finding it became the main goal of the Large Hadron Collider, LHC, at CERN. The LHC is a 27-kilometer ring of superconducting magnets built to slam protons together at 99.9999991% of the speed of light. The idea was to recreate, for a split second, the energy conditions of the early universe and see what might crawl out of the wreckage. After years of searching and sifting through trillions of collisions, on July 4th, 2012, scientists at CERN announced they'd found it. A new particle with a mass around 125 gigaelectron volts that behaved just like the theory predicted. The Higgs boson was real. The discovery was a massive win. It was the final piece of the Standard Model puzzle, confirming our understanding of how the universe gets its substance. But this triumph came with a deeply unsettling revelation. The precise mass of the Higgs boson wasn't just any number. It was a terrifyingly specific value, a number that puts our universe on a razor's edge, balanced precariously between lasting forever and suffering a sudden catastrophic collapse. The architect of our reality might also be a ticking time bomb. To understand why, we have to look past particles and into the unsettling concept of the false vacuum. In physics, systems are lazy. They always try to settle into their lowest possible energy state. A ball rolls down a hill and stops at the bottom. A stretched rubber band snaps back to its relaxed shape. This lowest energy, most stable state is called the ground state, or the true vacuum. In quantum field theory, the vacuum isn't empty space. It's the ground state for all the universal fields. It's the state of absolute, rock-bottom minimum energy. Our entire existence is built on the assumption that our universe is in the true vacuum. But what if it isn't? Imagine a huge, hilly landscape. The true vacuum is the deepest valley in the entire landscape. If you put a ball there, it's totally stable. It can't go any lower. But now, imagine a smaller, shallower valley, higher up on a plateau. If you put the ball in this little dip, it also seems stable. It'll settle at the bottom and stay put. As long as nothing pushes it, it's fine. But it's not in the lowest possible energy state. There's a deeper, more stable valley it could fall into. This state, seemingly stable but not truly stable, is called a metastable state. A universe in that condition is said to be in a false vacuum. The measured mass of the Higgs boson, combined with the mass of the top quark, strongly suggests this is exactly the situation our universe is in. The energy level of our Higgs field isn't in the deepest possible valley. It's resting in a shallow metastable dip. Our universe, with all its stars and galaxies, looks stable, but it might be a fragile illusion built on a foundation that could give way at any moment. A great real-world example is supercooled water. You can take pure water and carefully cool it below its freezing point. It will stay liquid in a metastable state. It looks like normal water, but it's energetically unstable. It wants to be ice, its true ground state at that temperature. All it takes is a single disturbance, a tap on the glass, one speck of dust, to trigger a violent phase transition. In an instant, a chain reaction of crystallization flashes through the liquid, turning it to solid ice. Our universe could be like that bottle of supercooled water. It exists, but it's primed for a change. And quantum mechanics provides a way for this to happen all on its own, through a bizarre process called quantum tunneling. At the quantum level, uncertainty is king. Particles can do things that are impossible in our everyday world. For instance, they can effectively borrow energy from the vacuum for a split second to overcome a barrier. Think of our ball in the shallow valley again. Classically, it needs a push to get over the hill to the deeper valley. But in the quantum world, there's a tiny but real probability that the ball can just vanish from its spot and reappear on the other side of the hill. It tunnels through the barrier. This means that somewhere out in the vastness of space, at any given moment, there's a chance a tiny patch of the Higgs field could spontaneously tunnel through the energy barrier, separating our false vacuum from the true vacuum. If that happens, a bubble of true vacuum would spring into existence, a bubble where the energy is lower. And as a result, the fundamental rules of reality are different. And once created, this bubble would be unstoppable. The creation of a true vacuum bubble would be the most catastrophic event possible in our universe. This process is called false vacuum decay. Once a bubble of this new, lower energy vacuum forms, it's automatically more stable than the space around it. As a result, it would expand outwards in all directions at nearly the speed of light. It would be a literal bubble of new physics, eating the old physics of our universe as it grows. To get a sense of the consequences, imagine you're playing chess. Suddenly, the rules change without warning. Pawns can now move like queens, and the board itself warps and melts. The game isn't just over. The very idea of the game is erased and replaced by something totally alien. That's a mild version of what would happen inside the bubble. Remember, the Higgs field gives particles their mass. Its value in our vacuum sets the properties of everything. Inside the true vacuum bubble, the Higgs field would have a different, lower value. This would rewrite the constants of nature. The masses of electrons and quarks would change. The strengths of the fundamental forces that hold atoms together could shift dramatically. What would this look like? It's hard to know for sure, but the educated guesses are all terrifying. The delicate balance that lets electrons orbit protons to form atoms might be shattered. If the electromagnetic force changed even slightly, atoms could fly apart or crush themselves into nothing. Chemistry as we know it would be impossible. Even protons and neutrons might become unstable, dissolving into a sea of other particles. Everything we see, stars, planets, us, is a product of our current physical laws. If those laws are canceled, all of those structures would be instantly erased. The new vacuum might not even support matter. It could be a realm of pure chaotic energy, or maybe new particles and forces would create structures so alien we can't even describe them. The change would be absolute. It wouldn't just be the end of life. It would be the end of the physics that makes life possible. This expansion of the true vacuum bubble is what's known as a first-order phase transition. And the scariest part is its speed. Because the bubble wall expands at nearly the speed of light, no warning could ever reach us. No flash in the sky, no alert from astronomers. Light itself can't outrun it. The universe would just be rewritten, one light year at a time, until the entire cosmos was converted. Picture a doomsday scenario. You probably imagine an asteroid hurtling toward Earth, a nearby star going supernova, or a global pandemic. In all those cases, there's a sequence of events. There's a before, a during, and an after. There's an awareness of the catastrophe as it unfolds. Vacuum decay is nothing like that. It's the ultimate silent instant apocalypse. The wall of the true vacuum bubble doesn't send a warning shot. It doesn't cast a shadow. Because it travels at or near the speed of light, its arrival and the information of its arrival are the exact same event. One moment, you exist. The next, you don't. The atoms in your body, the planet under your feet, the sun in the sky, and the entire galaxy would be simultaneously and instantly converted to the new physics of the true vacuum. There would be no flash, no heat, no shockwave. The concept of you would be gone before your brain could process a single thought. You couldn't even see it happen, because the laws of physics that allow for sight would be rewritten at the very moment the event reached you. It is an end that is, by its nature, unobservable. As the physicist Sidney Coleman, a pioneer in this field, grimly put it, vacuum decay is the ultimate ecological catastrophe. After the decay, not only is life as we know it impossible, but so is chemistry as we know it. This isn't an explosion that destroys things in our universe. This is a fundamental change to the universe itself. The space you occupied would still be there, but it would be governed by a new set of laws so profoundly different that the patterns of matter an energy that made you you would be fundamentally impossible. So, where could it start? Anywhere. A quantum fluctuation could trigger it in the Andromeda galaxy, and in 2.5 million years, the bubble would get here. Or it could happen in your living room, right now. Or it could have already happened 1 billion light years away, and the bubble wall is currently screaming through the void toward us, devouring everything in its path. We would have no way of knowing. The scale is as mind-boggling as its speed. Once started, the process would likely consume the entire observable universe and everything beyond. Every star, every black hole would be converted. The 13.8 billion year story of our cosmos would be erased and overwritten by a new and likely empty chapter. The only comfort, if you can call it that, is how ridiculously unlikely it is. But that brings up a chilling question. Could we, in our hunt for knowledge, accidentally cause our own doom? When the Large Hadron Collider was first about to be switched on, there was a ripple of fear that smashing particles with so much energy could create something catastrophic. One of the nightmare scenarios mentioned was exactly this: triggering vacuum decay. The fear was that by cramming so much energy into a tiny space, we might give the Higgs field the push it needs to fall into the true vacuum, creating a bubble of annihilation right here on Earth. If that happened, it would be the ultimate cosmic irony. In our search to understand reality, we would have accidentally destroyed it. The bubble would form, expand at the speed of light, and the Earth would vanish in less than 1/10 of a second, with the rest of the solar system gone minutes later. It's a horrifying thought, but, and this is a very important but, physicists are overwhelmingly confident this can happen. The LHC is safe. The reason is simple. Nature has already been running the same experiment for billions of years, with way more power than we could ever dream of. The Earth is constantly being hit by high-energy particles from space called cosmic rays. These particles are accelerated to insane speeds by violent cosmic events like exploding stars and black holes. The most powerful of these cosmic rays carry energies millions of times greater than the collisions at the LHC. These particles have been slamming into our atmosphere, the moon, and the sun for the universe's entire 13.8 billion year history. If a high-energy collision could trigger vacuum decay, it would have already happened. The universe would have been wiped out ages ago. The fact that we're here, on a planet that's been bathed in cosmic radiation for 4.5 billion years, is the best possible proof that our vacuum is stable against these kinds of events. The LHC, for all its might, is just recreating a type of event that happens naturally all the time, just in a controlled lab setting. Based on our current measurements, scientists can even calculate the theoretical lifetime of our false vacuum. The numbers are so huge, they're almost meaningless. The estimated lifetime of our metastable universe is trillions upon trillions of years, a timescale so vast that the universe will likely die of old-fashioned heat death long before vacuum decay becomes a threat. So, we can rest easy. Our scientific curiosity isn't going to end the world in this particular way. So, if we're not in any immediate danger, why does this idea even matter? Why do scientists and philosophers find the concept of a false vacuum so fascinating? Because it completely changes how we see our place in the cosmos. It tells us that our existence is fragile and contingent. The universe we live in, with its laws so perfectly tuned for life to emerge, might not be a permanent feature of reality. It might just be a lucky temporary phase. This idea has staggering philosophical implications. It forces us to ask, why are we here? If the universe is metastable, it means we won a cosmic lottery on an unimaginable scale. Out of all the possible energy states the Higgs field could have landed in, it settled in this one shallow valley, this temporary state that has lasted long enough for galaxies to form, stars to light up, and at least one planet to evolve creatures who can ponder their own improbable existence. It also hints that our own existence can be used as an argument for stability. This line of thought is called the anthropic principle. The very fact that we are here to observe the universe means the universe must have properties that allow observers to exist in the first place. The fact that the universe hasn't collapsed yet might mean the decay rate is so slow it's practically zero. Or, and this is what gets physicists excited, it could mean there's new physics we haven't discovered yet. Maybe there are other undiscovered particles or forces that help stabilize the Higgs potential, essentially building a higher wall around our valley and preventing it from ever collapsing. Theories like supersymmetry, for example, predict a whole new set of partner particles that could be exactly what's needed to shift our universe from metastable to truly stable. In this sense, the shakiness of the Higgs vacuum isn't just a threat, it's a clue. It's a giant arrow pointing toward undiscovered science, daring us to keep looking. The apparent lie of our universe may, in fact, be pointing us toward a deeper truth. We started this journey with a terrifying idea that our universe is a lie, a fragile illusion on the verge of collapse. We've traveled into the heart of particle physics, met the Higgs boson, and stared into the abyss of vacuum decay. We've learned that while our reality might be built on a metastable foundation, it's not something to lose sleep over. The time scale for this cosmic doomsday is so immense, it's irrelevant to us. But the value of this idea isn't in its ability to scare us. It's in its power to inspire awe. It reminds us that reality is far stranger, more complex, and more delicate than we can imagine. The fact that a single number, the mass of a single particle, can hold the key to both our existence and our potential annihilation is a deeply humbling thought. It highlights the miracle of our being here, in a universe of countless possibilities, where the tiniest tweak in the rules would have created an empty, sterile cosmos. We exist. We are the product of a delicate balance, a lucky break, a temporary state of being that has lasted long enough for us to look at the stars and wonder how it all works. The universe isn't a static stage, it's a dynamic, evolving place. And the story of the false vacuum is proof of how much we still have to learn. So instead of fear, let's feel wonder. The universe doesn't owe us stability. It doesn't owe us existence. And yet, here we are, thinking, questioning, and exploring the very fabric of the reality that made us possible.